Welcome to this session of Unit 2, Part 2. We're going to talk about Dalton's Law of Partial Pressures, and we're going to talk about collecting gas over water. And you're going to collect gas over water next week in the lab, so this will kind of be a good intro to that. What you should be able to get out of this is describe an appropriate procedure for collecting gas in water by water displacement or over water. You should be able to tell me any errors that may be associated with collecting a gas by water displacement. And you should be able to solve problems related to partial pressures of gases. So we're going to start with talking about what partial pressures are and how to calculate the partial pressure of a gas. So if you look at this diagram, if you have a container of oxygen gas and a container of nitrogen gas, you can get the pressure of the oxygen gas in its container, and you can get the pressure of nitrogen gas by itself in its container. If you were to then take these two gases and combine them in a different container that's of the same size, the pressure of the gas now in this mixture of gases would be equal to the pressure of the oxygen gas plus the pressure of the nitrogen gas in order to find the total pressure of the mixture of gases. So we're going to talk about how to find total pressure of gases in a mixture of gases and how to find individual partial pressures of gases. So partial pressures refer to the pressures of individual gases in a mixture. So for example, in this picture, if I asked you to find the partial pressure of nitrogen, I want to know what's the pressure of these gold molecules in the mixture, or what's the partial pressure of oxygen, what's the pressure of just the oxygen in this mixture. So Dalton's law of partial pressures says that if we have a mixture of gases, then the pressure of that mixture is equal to the sum of the pressures of the different individual gases that make up the mixture. Okay, and that equation is given right here. Total pressure is equal to the individual partial pressure of gas 1 plus the individual partial pressure of gas 2, so on and so forth. So in this diagram over right here, I've got a mixture of gases. This is gas 1, this is gas 2. So the total pressure inside of this container would be the sum of pressure of gas 1 plus the sum of pressure of gas 2. In some instances, you will know the total pressure of the mixture of gases, but you don't want that. You want the partial pressure of just one component in that mixture. If that's the case, you're going to want to use something called mole fraction. And mole fraction is indicated by this Greek letter chi. So mole fraction is like a percent, but you don't multiply by 100. It's part over whole. So for instance, let's say I wanted to know the mole fraction of gas A. What I would do is find the moles of gas A and then divide the moles of gas A by all of the moles of the different gases in my mixture. So if I had gases A, B, and C in my mixture, I would divide the moles of gas A by the sum of moles of A plus moles of B plus moles of C. Okay, so it's just part over whole. And there's going to be no units for mole fraction because your moles will cancel out. And you're not going to multiply by 100. The largest number you should ever have for mole fraction is 1 because we're talking about part of a whole. Okay, and a whole is equal to 1. So once you find the mole fraction, let's say you just want to know the partial pressure of gas A in a mixture. Partial pressure is equal to the mole fraction of A times the total pressure of A. The partial pressure of each gas in a mixture of gases in a container depends on the number of moles of that gas. Okay? The total pressure is the sum of all the partial pressures, and it also depends on the total moles of gas particles present, no matter what they are. So that's a way where you can find both the total pressure and partial pressure of gases in a mixture. So let's say you're given this problem. You have a mixture of hydrogen gas and oxygen gas, and the mixture contains 6.7 moles of hydrogen gas and 3.3 moles of oxygen gas. The mixture is in a 300-liter container at a temperature of 273 Kelvin, and the total pressure of the gas mixture is 0.75 atms. And let's say you were asked to calculate the partial pressure of hydrogen gas. There's more than one way to do this. So I'm going to show you the PV equals nRT method first, and then I'm going to show you a slightly simpler method to use. Okay? So if I just want to know the partial pressure of hydrogen, I would say pressure of hydrogen times volume equals moles of hydrogen times R times T. So this is just the ideal gas equation, except instead of total pressure and total moles, I just made this pressure of just hydrogen gas and moles of just hydrogen gas. So if I want to rearrange this to solve for just the pressure of hydrogen gas, I would have moles of hydrogen times R times T divided by V. Okay, so then you'd say I have 6.7 moles of hydrogen times the universal gas constant R times the temperature divided by the volume, and I would find that the partial pressure of hydrogen is 0.50 atms, and that kind of makes sense because there are more moles of hydrogen in the mixture than there are moles of oxygen. So if your total pressure is 0.75 atms, hydrogen should account for a larger partial pressure of that mixture. So that's one way to answer that question. You could also answer the question using Dalton's law of partial pressures and actually find the mole fraction of hydrogen, and then use that mole fraction to find just the partial pressure of the hydrogen gas. So I've done that for you here. So I just want the partial pressure of hydrogen gas. So I say pressure of the hydrogen gas is equal to total pressure times the mole fraction of, and that should say, I'm sorry, that right there should say hydrogen gas, not oxygen gas. So the total pressure is 0.75 atms, and for the mole fraction, there are 6.7 moles of hydrogen in a mixture of 6.7 moles plus 3.3 moles, so I'd add that together. So my partial pressure of hydrogen is 0.50 atms. Same as the other method, this is just slightly different. This gives you a different way to approach the problem. If you then wanted to know the partial pressure of oxygen gas, which you were not asked to do, you could say, well, I know the total pressure, and I just have two gases in this mixture. So the pressure of oxygen gas equals total pressure minus the pressure of the hydrogen gas that you just found. Okay, so the pressure of the oxygen gas would be 0.25 atms. So that's one way, or that's a different way to answer the question. Okay, now let's look at this. Let's say that we have one container with 24 liters of nitrogen gas at 2 atms of pressure. And we have another container with 12 liters of oxygen gas at 2 atms of pressure. The temperature of both gases is 273 Kelvin. If both gases are mixed into a 10-liter container, what are the partial pressures of nitrogen and oxygen in that resulting 10-liter container mixture? And what's the total pressure? Right, so one thing I think it might be easy for you to do, or just easier for you to see, would be to draw this out. So you've got a container of nitrogen gas at 2 atms, and that container is 24 liters. Then you have a different container of oxygen gas at a pressure of 2 atms, and that container is 12 liters. Then you're going to take nitrogen, this container here, and add it to a 10-liter container. And you're going to take oxygen and add it also to this 10-liter container. The nitrogen and the oxygen are not going to react. They are not going to have an effect on each other. But what will happen is I'm taking a gas at 24 liters and I'm putting it into a 10-liter container. So because my volume is decreasing, the pressure of the nitrogen gas is going to go above 2 atms. And same thing with the oxygen. I'm taking 12 liters of oxygen and forcing it into a 10-liter space. So this pressure is going to go up. So what I want to find out is when I move the nitrogen to this new container, what is its new pressure? And when I move oxygen to its new container, what is its new pressure? And then total, what's the total pressure of both the nitrogen and the oxygen together in the container? So again, there are different ways to do this problem. One way to do it is to use PV equals nRT. And I'm not showing this, but what you would have to do first is you would have to calculate the moles of nitrogen gas and the moles of oxygen gas, and then find the individual pressures of each of those gases. So you find the partial pressure of nitrogen and the partial pressure of oxygen. So you get your answers, and then you could add together those partial pressures to get the total pressure. So that's one way to do it. You're essentially having to use PV equals nRT 4 different times. Twice here, and then prior to this step, you had to use it to figure out your moles of nitrogen and your moles of oxygen. So that's a lot of equation manipulating, a lot of math work there. You could also, after you found your total moles of oxygen and nitrogen, you could add together moles of nitrogen and moles of oxygen and find the total pressure in the 10-liter container. And the total pressure would be 7.19 atms. And then to find the individual partial pressures, you could say partial pressure is equal to mole fraction of the gases times the total pressure. Again, that's a perfectly fine way to do it. You'll get the same answer, but it's just a lot of math work. So an even easier method to solve this problem would be to say, okay, temperature and moles of oxygen and moles of nitrogen are not changing. So in PV equals nRT, I am not changing N, I am not changing T, and R never changes. So the only thing I'm changing is P and V, pressure and volume. So I can eliminate the moles variable and the temperature variable. So I'm down to, I'm changing pressure and I'm changing volume. So P1 V1 equals P2 V2. And then I could solve for the new pressure of each individual gas. So basically, I could solve for, if I go from P1 V1 to P2 V2, P2 would be the pressure of the nitrogen gas. And I could do it again and find P2 for the oxygen gas, and then add everything together. So that's what I've done for you here. Okay, so I found for nitrogen, I did P1 V1 equals P2 V2, found pressure 2, and that's in that new 10-liter mixture, okay, as 4.80 atms. I do the same thing with oxygen, okay, and I'm solving for pressure 2. What's the pressure in that new 10-liter container? And I find that it's 2.40 atms. So I have the individual pressures of oxygen and of nitrogen. So to find the total pressure, I would just add those together. So I'd get 7.20 as my total pressure. And those answers are all the same. This way is slightly off. I mean, it's going to round to the same thing because I'm not using R, but you're still doing the same thing. I don't care which method you use. I just want you to be able to understand why you're doing what you're doing. And the method that you choose, you should be able to work easily and quickly. So if this method is quick on this slide right here, but if you don't understand it, I wouldn't use it. Use the method that you understand so that you get the right answer at the end. Okay? All right, so here is a problem where you have mixtures of helium and oxygen, and you are putting you're putting 46 liters of helium at a temperature of 25 degrees Celsius and a pressure of 1 atm, and then 12 liters of oxygen, same temp, same pressure, get pumped into a tank, into one tank of 5 liters. And then I said calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees Celsius. Okay, so here's another picture to help you visualize what's going on. So I have 12 liters of helium gas at 1 atm, and I have 46 liters of helium gas at 1 atm, and 12 liters of oxygen gas also at 1 atm. Okay, and I'm going to take these 46 liters of helium gas, and I'm going to push them into a 5-liter container. And I want to know, when I push 46 liters at 1 atm into 5 liters, what's my new pressure of helium? Okay, and then same thing with oxygen. I'm going to take 12 liters of oxygen and force them into 5 liters of space. So when I do that, what is my new pressure of oxygen? And then in this mixture, once both the helium and the oxygen are in there, what's the total pressure of both gases at the end? Okay, so pause me right now and work this out if you have not already, and then I'll go and show you the answer. All right, so I did P1V1 equals P2V2 for both gases. I'm looking for pressure 2, and pressure 2 refers to the pressure in that 5-liter mixture container. Okay, so I got the pressure of helium gas in the new container as being 9.2 atms, and the pressure of oxygen gas in the new container as being 2.4 atms. Okay, so that's the partial pressure of each gas, and then the total pressure, you just add the partials together to get the total. Okay, so that's how you do that. You can certainly use PV equals nRT for both gases, and then for the total mixture container, that's just a lot of work that's ultimately going to give you the same answer. And when time is of the essence, you want to move quickly and be right. Okay, so here's another problem. The partial pressure of oxygen was observed to be 156 torr in air, with a total atmospheric pressure of 743 torr. And you want to calculate the mole fraction of oxygen present. So based on the previous equation that you saw, partial pressure is equal to the total pressure times the mole fraction. So if I want to rearrange this equation, I divide both sides by the total pressure, PT. So the mole fraction of oxygen is the partial pressure of oxygen divided by the total pressure. Now, I've just plugged in the values from the problem. And then, so the mole fraction of oxygen is 0.210. And there are no units because my pressures are going to cancel out. Next problem. The mole fraction of nitrogen in the air is 0.7808. Calculate the partial pressure of nitrogen in the air when the atmospheric pressure is 760 torr. So you know the mole fraction of nitrogen, you know the total pressure, you just want the partial pressure of nitrogen. So same deal, partial pressure is equal to total pressure times mole fraction. Okay, and just plug in your numbers, and then there's your partial pressure of nitrogen, 593 torr. So here's a check for understanding to see if you get this. So you've got 3 different bulbs, each a different size and a different pressure of gas in each bulb. And these dials up here are called stopcocks. So they're closed initially. So if I were to open up these stopcocks, I want to know what would be the partial pressure of neon when all of the stopcocks are open. So basically when neon is able to flow through each branch in each bulb of this system. So what I would do if I were you is do P1V1 equals P2V2. So pressure 1 and volume 1 would be the pressure and the volume of neon originally when it's confined in this space. P2 and V2 would be after I've opened up all the stopcocks. So now my volume increases to 8 because I have a total of 3 liters plus 2 liters plus 3 liters. Now we're going to assume that these branches are part of the volumes that we've calculated that in, okay? And then my pressure is going to decrease because now I have more space, I have more volume for the neon to occupy, so it's not going to be as tightly compacted in this bulb. So the first pressure and the first volume of neon are 4 atms and 3 liters. The new volume is 8 liters, so my new pressure would be 1.50 atmospheres. Okay, here's another check for understanding. The figure above, and it's actually below, represents 3 sealed 1-liter vessels, each containing a different inert gas at 298 Kelvin. The word inert means it's non-reactive. Okay, so that means if I were to mix, which I'm going to, if I were to mix argon, neon, and helium together, they would not react with each other. They just stay in the container together, and total, they would produce a given pressure inside the new container. The pressure of argon in the first vessel is 2 atms. The ratio of the numbers of argon, neon, and helium atoms in the vessels is 2 to 1 to 6, respectively. After all the gases are combined in a previously evacuated 2-liter vessel, so that just means this 2-liter vessel is empty. There's nothing in it right now. What is the total pressure of the gases at 298 Kelvin? So right now, I know the partial pressure of each gas. I know that argon is 2 atms. And if you look at this, 1, 2, 3, 4 argon atoms caused a pressure of 2 atms. And they told me up here that the ratio of numbers of argon, neon, and helium are 2 to 1 to 6. So that would make me believe that 2 atoms of neon would create 1 atmosphere of pressure, and 12 atoms of helium would cause 6 atmospheres of pressure. So I know the partial pressure of each gas. So you could say P1 times V1 equals P2, which we don't know, times V2, which would be 2 liters. I'm sorry, I have to keep pausing you. They're yelling over the announcements. So you could say P1V1 equals P2V2 for each of the 3 gases, and then add together the total pressures at the end. What I've done for you here is said, okay, before moving into a 2-liter container, the total pressure of each of these gases is 2 atms plus 1 atm plus 6 atm, okay? And so that's a total pressure of 9 atms. And had we moved those 9 units of pressure into a 1-liter container, then my final total pressure would be 9 atms. But I'm not. I'm moving it into a 2-liter container. So my pressure is going to drop. So I'm going to take my total pressure and I'm going to divide it by my total volume, and that'll give me a final total pressure of 4.5 atms. Okay? All right, here's another check for understanding. So you have equal masses of hydrogen and oxygen gases are placed in a sealed container. What is the partial pressure of hydrogen gas if the total pressure in the container is 10 atms? So what I would do for this, I know the total pressure and I want to find the partial pressure. I would find the mole fraction of hydrogen. Problem is you don't have any numbers except for the total pressure. So what I did is I said I'm going to assume that I have 32 grams of each gas, and I did that because I know that 32 grams is equal to the molar mass of oxygen. So if you are solving a problem like this in your Kia, hint, pick the gas with the higher molar mass and say that your equal masses are that molar mass, okay? So that means if I have 32, and I pick this number again, if I have 32 grams of each gas, I have 1 mole of oxygen, and I have 32 grams divided by 2 grams per mole, so I have 16 moles of hydrogen. So my mole fraction of hydrogen is 16 divided by the sum of the moles, divided by 17. So my total pressure times the mole fraction would be equal to the partial pressure of the hydrogen in that system. And that makes a lot of sense because your total pressure is 10 atms. You have a total of 17 moles of gas in the container. Well, 16 of those 17 moles are hydrogen. So hydrogen should have a pretty big influence on your total pressure since you've got 16 moles of it compared to just 1 mole of oxygen. All right, I'm going to let you think about this one, and we'll talk about this answer in class tomorrow. I'm going to pause right here and start back in just a second.